This is lecture 24, and it's a continuation of the max-min word problems that we were talking about. In fact, it's a continuation of the last problem, the ideal beer can problem, except this time I want to do it again with cost figures put in. So let's suppose that the side of the can costs 5 cents per square inch, and the top and bottom of the can costs 7 cents per square inch. So remember, the can is made up of two circles, one for the top and one for the bottom. They're identical, although they don't look like it the way I drew it. And then a sheet of metal that is cut into a rectangle and then rolled to make the can. So the can looks like a cylinder, or is a cylinder. And we saw in the last lecture that it turns out that if you're minimizing the total surface area, then the answer turns out to be that the circumference and the height turn out to be equal, which makes for a very square can. But as I mentioned in class, if you tried to make this realistic, the cost per square inch of the top and bottom are going to be higher than the cost per square inch of the side, simply because every time you cut out a circle, you're going to have wasted metal, and you're going to pay more for that than for the sides. So if you just assume that the cost of the top and bottom is more, then let's see what happens. So the volume is still constant. In other words, it's fixed. And we know that the volume is pi r squared h. But this time, we're not interested in minimizing the area. We're interested in minimizing the cost. So the cost is the function that we want to minimize. So let's write this out. Minimize, I'll abbreviate that, minimize c. And the cost is going to be the cost of the top and the bottom plus the cost of the side. So if I have to figure that out, it's just 5 times the cost of the side. Now let's remember what this all is. This was h because it's the height of the can, and we have a radius r. So this is r here and here, of course. So the total circumference is 2 pi r. So we get 2 pi r for this times h is the area. So the area here is 2 pi r h, but the cost for that is 5 cents per square inch. So the cost for the side is going to be 5 cents per square inch times the number of square inches, which is 2 pi r. That's the cost just of the side. Then we have to add the cost of the top and the bottom. And those two costs are identical, so I'll double the cost of one of them. And one of them is 7 cents per square inch times the number of square inches, and the number of square inches, of course, is pi r squared. So pi r squared. So this is my cost function, but sorry, I made a mistake. 2 pi r h. I knew there's an h in here somewhere. So again, 5 times the cost of the side. The cost of the side is the area in square inches times the cost, which is 5. So there's the 5 times 2 pi r h. That's the area of the side. Plus 2 of these guys, which are each 7 cents per square inch times pi r squared, square inches for a circle. And this cost is now a function of both r and h, so I'm going to have to get rid of one of those. And I'm going to get rid of h, obviously because I only have it once, and because it's also easy to solve for. So h is equal to v over pi r squared. So our cost is going to be 10 pi r times v over pi r squared plus 14 pi r squared, which can also be simplified as, let's see, the pi's cancel, and we're left with 10v over r plus 14 pi r squared. So now I have the cost as a function only of r, and I can go ahead and figure out what the critical numbers are for this. Also, you might note that the smallest value for r is 0, and then there is a largest value of r, which I probably should figure out. But in any case, let's see what we're going to get here for the derivative. If we calculate, I've done this before, this is going to be minus 10v over r squared, and the derivative here is 28 pi r, and that's the derivative. We set that equal to 0 and solve. So that's going to be 28 pi r equals 10v over r squared, and so r cubed, moving the r squared over to that side, is equal to 10v over 28 pi. So r, and 10 over 28 of course reduces a little bit to 5 over 14. That doesn't much matter. But this is a constant, 5v over 14 pi, whatever that is. And so r is going to be the cube root of 5v over 14 pi. Which of course doesn't help us too much in terms of figuring out what's going on. But I bet if we go back to this equation, r cubed equals 5v over 14 pi, and plug in v as we did before, v is equal to pi r squared h. So if we look at that, this is going to be r cubed equals 5 times pi r squared h, that's our v, divided by 14 pi. And let's see, that should reduce nicely. We can divide both sides by r squared, leaving us, whoops, this isn't going to be equal to anything. I'm going to end up with r equal to, because I divide both sides by r squared, and I get 5 over 14, and the pi's are gone, and the h is still there. So look at what this is telling us, that our radius is 5/14 times the height. Now of course the radius is half of the diameter, so if we double both sides, this is going to tell us that the diameter is going to be 10 over 14 times the height. And so you can see from here that the can has gotten narrower because the diameter is only 10/14, or what, I'm sorry, 10/14, which is 5/7 of the height. So we reduce the height by 5/7, and that gives us the diameter. So the diameter is smaller than the height. The diameter will be only 5/7 of the height, and that makes the can get taller, which is more normal. And that corresponds to what you see mostly with cans. You see very few cans that are squat, short and fat. Okay, so this illustrates a couple of things. It illustrates the idea of how the cost figures allow us to get the more reasonable results, but more importantly, we get to see how you could handle the cost in the first place by realizing that it's a problem in minimization. You are minimizing the cost. So the most important part of this problem is right at the beginning. All this algebra and calculus stuff here doesn't matter as much as setting up the problem right in the first place. Get the cost figured correctly, and the cost depends on the metal that you're using, and each has a different cost associated with it, so you sum up all the costs and that gives you the total cost. Get that as a function of one variable by eliminating, in this case eliminating the h, so that it's all down to r. And you look for a way to eliminate variables by looking for another equation, another relationship among the variables. And in this case, that relationship comes from having a fixed or constant or a determined volume. And that volume equation then represents a relationship between r and h. As soon as you know that v is constant, if you make a change in h, that's going to force r to dance. Make h bigger, r has to get smaller. Make h smaller, r has to get bigger, and vice versa. So that's the relationship between the two, and that allows you to eliminate one for the other one. Okay, let's try another problem. This problem, I'm going to ask you to pause and get your book, because I'm not going to write the problem out, but I want you to look up in the textbook for the statement of the problem. And the statement of the problem is actually on page 329, and it's the boat problem, the boat and the runner. So it's the example 4 in the textbook, and I just want to do it the way I think about it. And you can follow it along in the book if you'd rather, but I have a very slightly different way of thinking about it, and maybe a slightly different way of actually pulling it off, if I can do this the way I'm thinking. All right, so pause the video, go get your book, and read the description. So I'm going to draw the picture for this problem slightly differently, because I think of the river going this way, just because that's the way I think of it. So there's the river, and the man is here when he starts, and that's your point A. And he's going to row across the river, and he's got to end up down at this point. And I guess that's what the book calls B. So this is point A, and this is point B. B is his destination. So he's got to get there, and he can get there by rowing all the way, or he could row straight across and then run the rest of the way, or he could row part way across and then run the rest of the way. So I'm going to draw something in the middle as his path. And so the diagram that we're going to have is this kind of diagram where we've got a distance this way, and a distance this way that's going to be determined, and we can draw straight across this way, just draw all kinds of segments so that we get a decent picture. This becomes a right angle here, because I'm going straight across the river at this point, and I can even connect the dots this way over there. So we'll make the dot right on the river in both cases. The river runs through the dot. Okay, so he can choose to go anywhere from this way to this way, but he's not going to go any other way. He's not going to come down this way and back because he rows slower than he runs, and it makes no sense for him to go this way because it's a longer distance, and so he's going to take longer. So the problem, if you think about it just for a moment, is very simple in terms of what it is that you're supposed to do. You read the problem description. Where should he land in order to reach B as soon as possible? Sounds like you're trying to locate this point here, find, I think they even call it D. I'll go ahead and be consistent with the book's language. They want to find this point D, but that's not really the problem. They're misleading you a little bit, because the question is not a problem of, it is, you will find D, but the question, if you read it, is where should he land to reach B as soon as possible? All of these problems are max-min problems. So in every single problem, one of the first things that you should do, you can draw the picture first, you can read it, you can identify some variables, but very, very early on, you need to identify something that is to be minimized or maximized. So what is it that you are minimizing in this problem? It's as soon as possible. So what we want to do is minimize the total amount of time. And that's maybe the hardest part of the problem right there, because you have to figure out how much time it's going to take him to get from A to B, depending on how he goes. So he's going to take some time rowing, and he's going to take some time running. So here's a way to think of the total time. The total time is the time rowing plus the time running. Oops. Okay. Now, that's a difficult thing to come up with, but it's very logical if you think about every problem that's a max-min problem is a problem in optimizing. Optimizing means getting the most out of something. So doing the best you can. In this case, finding the best time possible, the fastest time. Of course, if you're a runner, you're interested in that. Fastest time, your best time. Here, the guy is interested in minimizing the total amount of time it takes him to get from A to B. Yes, we have to figure out where that point D is, but it's the total time that we are trying to minimize. All right? And we need to remember one important fact, that distance equals rate times time. And so we can figure out what time is by dividing distance by rate. And since they tell us in this problem what the rates are, he can, let's see, it says he can run 8 kilometers per hour and he can row 6 kilometers per hour. That's pretty fast, actually, for rowing at least. 6 kilometers per hour is the speed for rowing, and 8 is the speed for running. Now, that's not the time. Those are the speeds. But we can get the time if we know the distances. So that tells us that we need to know the distance that he's rowing, which would be this distance, and the distance that he's running, which would be this distance. So if we just call this distance x and this distance y. Now, I don't know that that's what they did, but that's what I'm going to do. I'm going to call this distance y because it makes sense to me. That's the distance that I'm going to be rowing, and that's the distance that I'm going to be running. Now, it's two variables right now, but we'll worry about that later. So my total time I can figure now as the time rowing, which is going to be the distance rowing, y, divided by the rate, which is 6, plus the time running, which is the distance that I'm going to run, which is x, divided by the rate, the speed at which I can run, and that's 8. Okay, so time is now, isn't this backwards? We were doing so many problems where time is the independent variable. Here, time is the dependent variable. I told you this was going to happen sooner or later. Time is dependent, but it's dependent on too many variables, x and y. So we have to look for a way to get rid of one of these variables. And that's going to come from the geometry of this picture, because I haven't worked everything into the picture. So first of all, the river is 3 kilometers wide, so the distance from here to here is 3. It's also the distance from here to here, of course. And he wants to reach the point B, which is 8 kilometers downstream from where he is. So if this is downstream, then the distance from here to here is 8. So I don't have a way to put that easily on here. Let's do this. 8 is from here to there. All right, now I've already got x, and then I can figure out what this is, because this is now going to be 8 minus x. So 8 minus x goes from here to here. So I can figure a relationship between x and y. I can see it already, because the relationship between x and y is from the Pythagorean theorem coming out of this little triangle right here, because I've got x and y in the same triangle. So if I just write that down, I'm going to have y squared, which is the hypotenuse, equal to 3 squared plus 8 minus x squared. So that allows me to eliminate one or the other of the variables. I think I'll eliminate y. So y equals the square root of 9 plus 8 minus x squared. Now wouldn't we love to get rid of, to distribute that square root and write that as 3 plus 8 minus x? Nah, no such luck. Radicals do not distribute over addition. This is a crucifiable offense. Just, you have to leave it this way. It's not something you can simplify. Sorry. But this is our value for y, and so I can stick it in here and write the square root of 9 plus 8 minus x squared over 6 plus x over 8. Right? And that's our total time. And that is what is to be minimized. Now, at this point, I want you to sit back and sort of, if you followed all of this, you can sit back and pat yourself on the back and say, you know, in a sense, the problem's over. From here on, it's stuff that we've already been doing. We can analyze this function using calculus. In fact, what I could do is just put this into Maple and ask Maple to graph this for me to see what's going on, and make Maple do all the calculus for me, so that we don't get bogged down right now in the calculations. All right? Now you can see already that this is way too hard a problem for me to ever stick on a test if you have to take it further than here, because taking the derivative of this is no fun at all. Then you have to set it equal to 0, then you have to solve, and you know, you have to figure out whether you're dealing with maxes, mins, whatever, and figure out the endpoints. The endpoints, by the way, are interesting here. What are the endpoints for the variable x? Well, the largest that x could be is 8, right? The distance from here to there could be, I mean, this point D is the distance from B, where the guy has to end up, to where he chooses to land. So the farthest that x could be is here. It makes no sense to go there or that way. No, we're going to go straight across and then that way. So this would correspond to rowing the least amount and then running the rest of the way. So x could be as big as 8. So we got to check that out. We got to think about what's going to happen when x is 8. But we could decide to row all the way and run not at all, which would mean that x would be 0. So the domain of this function t, where it's written in terms of x, the domain of this function t is all x is between 0 and 8. So we're going to have to worry about those endpoints. In fact, we can do that now. If we calculate the time that it would take if we plugged in 0, that would mean x is 0, so we are not going to run at all. We're just going to row straight across. And the total time will then be, you plug in 0 for x, and you get 8 minus 0 is 8, squared is 64, plus 9, 64 and 9 is 73, so I get the square root of 73 over 6, and then this term is 0 over 8. So square root of 73 is 8 something, so it's 8 over 6. Okay? What would t of 8 be? And what would that mean? It's the time that it would take if x is equal to 8. X equals 8 corresponds to you choose to go straight across the river and not row any more than that. So you're going to row this much and then run the rest of the way. So how much time is that going to take you? Well, you just plug into your formula. X equals 8. So this term goes away, and you're left with the square root of 9, which is 3, over 6, which is 3 over 6 is 1/2, plus, now you've got 8 over 8, which is 1. So this is 1 1/2, 1.5. Compared to, what was this? This is 8. So it looks like 8 over 6 is a little bit less than 1 1/2. So it looks like you're going to be doing better with 0. But we still have a critical point to find. So we have not analyzed this total time function. So let's go ahead and put this into Maple rather than trying to do that work ourselves. So I'm going to have to flip back and forth between this screen and the Maple screen so that I can figure out what I'm typing in. So we're going to type in the square root of 9 plus 8 minus x squared. So we're going to have the square root of, I forgot it already, the square root of 9 plus 8 minus x squared. 9 plus 8 minus x squared divided by 6, I believe, plus, if I remember correctly, x over 8. Let me just double check that. X over 8, 9 plus 8 minus x squared over 6. Right, so that is my function that I want to deal with. All right, and that looks about right. And now what I want to do is differentiate that. So I right-click and go to differentiate with respect to x. And there's the derivative. Okay, what are we dealing with? Well, the denominator could be nasty at times, but I'm really interested just in that minus 16 plus 2x. Ooh, but there's a plus 8. All right, Maple, solve this for me. Actually, I'm taking a shortcut here because I don't have an equation, but Maple assumes that I am setting this equal to 0. So this is my solution. What is that approximately? Oh, doesn't it tell me? Maybe not. All right, let's just grab it. And put it into a math box. And I bet now I can approximate it. Yes. So I can approximate it, and it comes out to about 4.5. 4.5. So, going back to this, going back to here, we have that we've set this equal to 0 and found that x equals that messy thing, which is about 4.5. Now that's x that's 4.5. And if you look at your picture, that should make some kind of sense. We have a critical point for this function at x equal to 4.5, so about halfway there. Now what we have to do is figure out what this kind of critical point is, and since I've got Maple, I'm going to go ahead and take the second derivative and see what that is, and I'll also graph it while we're at it. So we'll go and say, first, before I forget, let's graph this thing and just do a quick plot and see if we get lucky. There we go. Okay, so obviously our x can be anywhere from 0 to, we said, 8. So it looks like we're going to get a minimum right around here. Now I could zoom in, but I don't really care to do that. We're just going to do the analysis. We already know that x equals 4.5, and you can see that that's what's happening here. Right around 4.5, we're getting, or 4.6, we're getting our minimum value, which looks like it's going to be close to 0. But what kind of critical point is it? Well, it looks like a min. We could prove that it's a min if we differentiate that. Oops, we already differentiated it. Yes, this is the derivative. I want to differentiate it one more time. This is the second derivative down here. And at this point, I will evaluate that second derivative at the critical point. I wonder if I can do this. Copy this guy and evaluate this at a point. Will it let me paste it in? Yes. So I'll do that and approximate that for me. That is 0.01. Now why did I do that? I just wanted to know whether it's positive or negative. The answer is it's positive. Well, of course, it's a concave up curve, so that makes this a min. If you look at the graph, then yes, of course it's a min. And what is the value at that critical point? So I'll take that same value and plug it into the function that we had here. So let's evaluate at a point, and again paste that value in. And it tells me this is the y value. Approximate that, please. And that's about 1.3. Okay, so coming back to our page here, we can say that when x is approximately 4.5, then t at this point is about 1.3. Now I need to look at what this number is. Square root of 73 over 6. Back to Maple, what is that? Square root of 73 over 6. Oops. Over 6. And approximate that for me, please. And that is 1.42. So, what that tells me is that this is about 1.4, this is about 1.5, and this is 1.3. So, in fact, if we go with x equal to about 4.5, so about 4.5 kilometers away from B, and choose that point, and row to that point, and run the rest of the way, we will minimize our time. Our time will only be 1.3 or thereabouts, whereas if we had rowed the minimum, which is to go straight across and run the rest of the way, that would have been x equals 8, and it would have taken us 1.5. And if we'd rowed all the way, if we had rowed, R-O-W-E-D, all the way, then it would have taken us 1.42. By the way, the units here are kilometers per hour, and so we're talking about these figures being hours, 1.3 hours as opposed to 1.42 hours, as opposed to 1.5 hours. So the difference is about 2/10 of an hour or 1/10 of an hour, so about 6 minutes or thereabouts, 12 minutes. Okay, so that's enough for now. We've done a couple of problems, and maybe we'll do a few more at some other point.